Hey gang, welcome back for another video here on Stereochem. Okay gang, so if you're watching this, then it's safe to assume that you are in the dark depths, the very end of organic chemistry 2. So I just want to take a second to say congratulations, because if you're here, that means you've endured some battles and you may have some scars to show for it, but nothing to be ashamed of. It only shows that you've weathered the storm, you've put in the hours, and that you're stronger because of it. So just first and foremost, I want to say congrats. And this part of organic chemistry is a bit interesting because it doesn't really, there's not a lot of mechanistic stuff going on. It's a little bit different than things we've done in the past. It's kind of knowing concepts. It's where organic chemistry and biology start to kind of, converge together. So if you're a biology person, then you might like this part of organic chemistry. If you're not a biology person, I'm sorry, but you're gonna have to learn it anyways if you're watching this video, obviously. So what I wanna do is this video is all about an introduction to amino acids. Kind of why are they called amino acids, some basic, properties of amino acids, characteristics, as well as some terminology that will be very important and terminology that is necessary for you to, intelligently speak about amino acids when you're doing organic chemistry or probably biology too as well. So let's dive in. Not a crazy, in-depth video, but I think an important one nonetheless. So amino acids have this general structure, and this is probably the only time you're going to see me draw what I'm about to draw like this. But amino acids roughly have this type of shape. Yeah, right here. I'll switch these two. It doesn't really matter, but the point being, it makes sense that amino acids, right? There's an acidic part of this, and then there's an acid part and component, and then there's an amine component, right? And you can see that. So an amino acid, one amino acid unit, is gonna always have and if you know a little bit more about amino acids, don't worry. I didn't draw this completely accurate, but you have some NH2 portion. It might be an NH3+. You have this carboxylic acid, right? Carboxylic acid. You'll have an amine. You can have this R group. This is commonly referred to as a side chain. And then you'll have a hydrogen, right? So the side chain can be various different things. You always have the amine, you always have the carboxylic acid, you always have the hydrogen when you have one unit. Okay, so other words for amino acids, people like to call these alpha amino acids. And that makes sense, right? Because if we're looking at this right here, from there's a carbonyl here, right? And because we know organic chemistry, we know that this right here is the alpha position. And on the alpha position, right, that's the carbon that's attached to the amine, right? So an alpha amino acid just means alpha to the carboxylic acid, there is an amine. People also like to call these two amino acids. And, commonly people will say amino acids, but what's also important is that this carbon right here is referred to as C2. You will see that, people refer to that very often. So obviously it's because it's the second carbon. If we're numbering, we're starting at the carboxylic acid carbon. Okay, so amino acids, there are more than 500 that exist in nature. However, for the purposes of organic chemistry, whenever this is covered in a class, right, you're going to hear a lot about the 20 essential amino acids. So these are amino acids, I'm going to abbreviate AA. These are amino acids that humans, in your diet, you will get these, and they are necessary for life. So what's unfortunate, this is my personal gripe with organic chemistry, but it's, when you're in a class and you're being tested based on the knowledge in that class, I would say to be safe, unless your professor tells you otherwise, these 20 essential amino acids, memorize their structures, the names of them. There are things called abbreviations. You should know those as well. So it is annoying, know all 20, be able to just draw them. If I say alanine, you should know what that looks like. You should know that for alanine, this is how it's spelled. But alanine is abbreviated like this. When I mean abbreviation is that this is the common, like it's usually 3 letters. There are shorter abbreviations, but I feel like you will probably be expected to know the 3-letter abbreviations for amino acids. So there's 20 of them. It's not terrible, but you know, to be on the top of your game, to get the best grade possible, which is the goal, right? If you're watching this video, that means you care about your grade. So just put the time in, memorize them, know your essential amino acids, okay? So I think that was that's all like the public service announcement I kind of wanted to do as far as knowing them. So I'm gonna erase this, but I wanna continue to talk about characteristics of amino acids. So the 20 essential amino acids, that's kind of what we're gonna be talking about moving forward. AA, you're gonna see me use AA as an abbreviation for amino acid. So when you have, so now I'm going to draw, and don't worry that I'm drawing these with charges. If you want to know why, you better go ahead and watch the Stereochem video where we talk about isoelectric pH as well as how amino acids look in various pHs. But I'm just doing this because it's a very common way to express amino acids. So if we take a look at this, I'm using this R right here, but it's important to note that essential amino acids in nature, they exist with an S configuration, an S stereogenic configuration at carbon 2. So if you draw an amino acid, for example, let's draw alanine. And alanine is just, the R group is a CH3. So if I'm going to draw alanine, so let's say right here, so I'm going to connect these, but I have not drawn any, wedges or dashes, right? So I've not depicted any stereochemistry here. So how can I appropriately show, if I wanted to show that this is S-alanine, how can I show that, right? Well, right, when you do stereochemistry assigning with amino acids, right, if we look at this, your first priority group is always, take this to the bank, going to be the nitrogen. Because whether it's your R group or this, right, the first thing that this carbon is going to be bonded to, it will always be bonded to a nitrogen. It will never be bonded to anything that weighs heavier than a nitrogen. Nitrogen is always first. There's only one situation where your R group's going to be heavier than this, and I will talk about that. However, if we look at this, right, we're assigning priority. We know that we have a carbon and carbon tie, but this carbon is attached to, it's double bonded to an oxygen as well as single bonded to an oxygen, and this carbon is attached to 3 hydrogens. So our second priority lies here, and our third priority lies here. So if I'm trying to draw S-alanine, right, if I follow my priority groups, I'm turning my Stereochem wheel to the right. That is not the correct way. But if we look this way and we are actually assigning this way, so I need to kind of invert my stereochemistry. So I need instead of my lowest priority group facing away from me, I need this hydrogen to be a wedge, and I need the CH3 group to be a dash. So now, right, I look like R, but we're actually S here, okay? So when you're looking at amino acids, if someone tells you to draw the S version of something, right, we can absolutely draw R-alanine. And actually what that looks like, right, I just have to actually switch that, I have to make that methyl group wedged and the hydrogen dashed, right? So it would look like this. I keep my amino group and my deprotonated carboxylic acid, my carboxylate like that. And then in fact, all I have to do, and it doesn't matter that I'm drawing the CH3 differently, but I can have it like this, because if I was going to say, all right, can I double check myself that this is R-alanine? Then all I would need to say is, okay, yep, the nitrogen is priority 1, this is priority 2, because that carbon right here, even though it's tied here, it wins out because of its bonds to oxygen. My methyl group is priority number 3. I'm turning my wheel, I'm going to the right, right, from 1 to 2 to 3, and it looks R, and it actually is R because our lowest priority group, the hydrogen, is facing away from us, okay? So, like I said, anyone can ask you to draw blank amino acid name, R or S amino acid name, right? And then you just need to know how that works, right? Based on, you actually need to know the structure, and then you need to be very comfortable with assigning R and S like that. Now, what I want to do, I'm going to actually clean this up a little bit. I want to introduce a little bit of more terminology. We're actually going to, right, there's R and S here. I want to actually explain, people very commonly refer to L and D type of amino acids, and it's very, very, very similar to what's going on right here, and it kind of melds together with our knowledge of carbohydrates. So give me 1 second, I'm going to erase this, and then we'll talk about it. Okay, gang, now that we have, through alanine, looked at, drawing an amino acid on flat, with bond line right here, and we've seen that, we can assign R and S, and we've also discussed that S is, the typical stereochemistry that you see at C2, I want to introduce a new, some more terminology, because people love to refer to amino acids as L or D. And it's almost the same as R and S, you'll see what I mean, but this is going to rely a little bit on our carbohydrate knowledge. So with L and D, when you use this terminology, we are drawing Fischer projections. So if you thought Fischer projections were dead, they are back one last time, okay? So when we draw L and D, right, so clearly what we have going on here is, if we're going to use alanine as a first example, we're going to do more than one. Much like carbohydrates, we have a convention. The convention is that you put your you put the carbonyl up top, a carboxylic acid, right? Then what you will do, right, is we have 4 things. So clearly we're going to have, this is C2 right here. So then what you do is you put your R group always at the bottom. That's always going to be the case. So here our R group is just the CH3, right? Then if you have L, that is what's going to determine what you're going on here. Your amino group is placed based on L or D. If it's L, your amino group is on the left, right? Very similar to carbohydrates and the last OH, right? So here we have this, and then obviously the only thing left is a hydrogen, right? And we can still do, we can kind of see, we see this L configuration, but we can also, based on this now, we can see, okay, just because you have S does not mean it's L. And just because you have R does not mean it's D, right? So we can see with L-alanine here. So this is S-alanine, right? For L-alanine, we can see what the stereochemistry is at C2. So remember, priority 1 goes to the amino group. Priority 2 goes to the, carboxylic acid, deprotonated here. And then finally, we have our R group, which is priority number 3. So remember, right, we look like R, but remember with Fischer projections, these things that are going across, they are arms coming out to hug you, and these two are things going away from you, right? So our lowest priority group is coming out towards us. So we look R, but we are actually S, okay? So L-alanine has an S configuration. This is S-alanine. So we see in the Fischer projection very clearly that this is L-alanine, right? Because we see that the amino group is on the left. But, if we wanted to represent it in a, flat paper, straight chain type fashion, right? This is L-alanine. These are the same is what I'm getting at. So if we want to do D, all we need to do, without, don't have to assign stereochemistry, but when you have a D amino acid, your amino group is on the right. Okay? So then your R group always goes on bottom, and obviously your hydrogen goes opposite the amine. So we already assigned the stereochemistry with L, so we know, since we're just doing a single switch here, right, this D amino acid at C2 is R. So you can see that we can draw amino acids and we can label them R and S. And if anyone specifically asks for L and D, right, you can represent that with a Fischer projection, okay? So what I want to do is look at two different amino acids, draw their R and S in a straight chain, type fashion, and then I want to draw their D and L configurations as well. So 2 examples, and then calling this video a wrap. Okay, gang, so what I want to do here, I want to take a look at the amino acid called tyrosine, and I want to do 4 things. I want to represent S-tyrosine, R-tyrosine, just in a flat, straight chain fashion. And then I want to draw the Fischer projections for D and L tyrosine. And then I want to talk about how S and, the relationships between S and R and D and L. Because there is like an almost rule. You'll see what I mean. Okay, so I know we have again, if I'm going to draw this, doesn't matter that these are charged, but it's okay. So we can draw this confidently. And I would encourage you to do this. Okay, so my R group is this little monster over here. So this would be the amino acid. So you have a carbon, then you have a benzene ring, and then you have this OH group off of your benzene ring, right? So if you can see, I have my amine right here, then I have my C2 carbon, then I have my carboxylic acid, and then off of C2, I have my R group, right? You can see that I'm going to dot this carbon, and that is this one inside the R group. Then I have a hydrogen, right? So structurally, right, I've connected everybody properly in this amino acid, but I want to represent, first let's tackle S-tyrosine. So how does that look? We need to assign stereochemistry. So remember, the highest priority thing straight off of this carbon is the nitrogen, okay? Then I need to compare my, carboxylic acid with my R group, and you can see that the carboxylic acid bonded to oxygen 3 times, right? 2 from the double bond, 1 from the single bond. Definitely beats out this carbon right here that's attached to this carbon down here and 2 hydrogens. So priority 2 is with the carboxylic acid. R group is a 3. So we look R, right? But we want to be S. So we need to look like R, but we want to be S. So our lowest priority group needs to actually face us, so we get the opposite of what we look like. So for S-tyrosine, we look like this. Okay? So once you get 1, it's super to, represent the second. So I'm going to erase this now. To represent R-tyrosine, all you need to do is flip the wedges and dashes for your R group and your hydrogen, right? So now the R group is what's wedged. And our hydrogen is dashed, right? So then we look like R and we actually are R, right? Turn the wheel to the right. We got an R, okay? So now here's what I think is the new, more important part, right? D and L, what are we doing? Right, so remember, our convention for drawing D and L goes as follows, right? We make our Fischer projection right here. Remember, carboxylic acid goes on top. And since we're dealing with L, our amine group is going to go on the left. Okay? Our group always goes on the bottom, so we have this thing, which I did not give myself enough room to draw, so I apologize that it's small. And hydrogen over here, okay? So remember, so now I want to figure out in L-alanine, right? Now this is just I think I did a poor job of explaining this before. L and D is like a convention. And L and D does not speak about the stereochemistry at C2, right? S and R is absolute. L and D is something that people kind of made up and said this is a convention we will follow, okay? So what is the stereochemistry in L-tyrosine? Well, remember, we have 1, 2, whoops, counting is hard, 2 and 3. So we look R, but remember, H is coming out to hug us, so we are actually S here, okay? And then over on the D side, right? Remember, carboxylic acid goes on top because we are D, the amine group goes on the right-hand side, amino goes on the right, and the R group goes on bottom. hydrogen gets filled in, okay? So remember, let's like see what the stereochemistry is at D, and remember, 1, 2, 3, priority groups didn't change. So we look S, but remember, hydrogen's coming out to hug us. So we look S, but we are R, okay? So what you're gonna see, and what I wanna try and prove to you, is except for one case that I will show you right after this. One case, and this is for essential amino acids. I want to make that very important. Except for one case, I'm going to say for essential amino acids, S equals L, like your L amino acids will be S at C2. Let me write that differently. I feel like I'll say L amino acids are S, and then we can say D amino acids are R, okay? Except for one case. And what is that one case? Well, that bad boy who does not follow the rules is named cysteine, and we will see why that is the case once I clean this up. Okay, gang, to round out this video, I just want to talk about cysteine, who does not play by that nice rule we just kind of established in the previously. Okay, so cysteine. If we look at what the R group is for cysteine, right, we have it's just going to be, it's just a carbon, CH2, and it's directly bonded to a sulfur, okay? And you're going to see that that is what makes the difference and why cysteine doesn't fit into that nice rule we were talking about. Okay, so if I wanted to draw S-cysteine, here's how I could go about doing it, right? I know I have my template. I have this, and I know I'm going to have an H, and then this R group, which is a carbon, and then right off that carbon I have a sulfur and a hydrogen, okay? So now here's where things get wacky, and here's the only time this happens with your essential amino acids, right? We know that directly off of C2 when we're assigning stereochemistry, the thing that wins out, right? We have carbon, carbon, nitrogen wins. Always, 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 right? But it's at this point where things get different. Here we have a tie between carbon and carbon, and this carbon is touting 3 bonds to oxygen, right? This carbon it's a carbonyl, so it has 2 bonds to oxygen as well as that third oxygen. However, let me make these a little darker. However, this carbon right here is bonded to a sulfur hydrogen hydrogen. So the R group actually has a higher priority here than the carboxylic acid component. And that's the difference. Okay, obviously hydrogen always comes in dead last because it's hydrogen, come on. Okay, so if we're trying to assign an S stereochemistry at this position, and we know this is how our priority chain goes. If we look at this, we look S. So I need to actually make sure that my hydrogen is facing away from us, and I need to make sure that this is a wedge. And that's a terrible way to, there we go. Okay, cool. So that is S cysteine. So now that I've gotten S, I don't need to do that whole analysis again. I can just flip the wedge and the dash here to get R. So if I do NH3+, I have my carboxylic acid component. I know now I need to dash the R group side chain, and then I can wedge my hydrogen because I know the priority goes 1, 2, and 3, and I look S, but I'm actually R because the lowest priority group faces us. Now, here's where things get interesting. Here's where we will demonstrate why cysteine doesn't follow the rule, and it's because of the fact that the sulfur is present, okay? So if we look at L, we previously said that L amino acids are S at C2, and we were saying D amino acids are R at C2. So obviously we're expecting to see this L cysteine to be R and the D cysteine to be S, okay? So remember, our convention, carboxylic acid, carbonyl goes up top. We're dealing with L, so amino group is on the left, R is on the bottom. So I have a carbon, and and I have my SH, and then hydrogen goes opposite of the amino group. So remember, priority goes 1, then the R group, and then this. So we're looking S, right? However, this is coming out to hug us. So we look S, but we are in fact R, which is what we expected because this is the exception, okay? And now, if we do this over here, remember, D, amino group goes on the right, and R group goes on bottom, H over here. So again, we don't even have to do this because we found out this is R and D is the opposite. However, 1, 2, and 3, we look R, but we are actually S because we need to take the opposite because hydrogen's facing us. So I know this video was a little bit longer, gang, but I think it really pays to understand amino acids can be called alpha amino acids or 2 amino acids, right? They're called amino acids because of the fact that they have this amino presence. They have an acid, a carboxylic acid component. The S configuration is what is most found in nature. Remember, there are over 500 of these things that occur, but there are 20 that are the rock stars, right? 20 especially that are super important to humans, to us. We need to get them through our diet. And, right, we said S configuration at C2 is what's commonly found in nature, and we can represent amino acids in this flat, in a fashion that we usually draw our structures in organic chemistry, but there's also a convention to represent them in Fischer projections. And that convention, we label them with L and D, but that tells us nothing about their stereochemistry, right? And we discovered that because the priority chain usually goes amino group, carboxylic acid, R group, right? We saw that almost always L amino acids have an S configuration at C2 and D amino acids have an R configuration at C2. However, there's one exception to that rule within the realm of our essential amino acids. That outlaw is cysteine, and it boils down to the fact that the R group is a higher priority than the carboxylic acid because of the sulfur that is attached, to the first carbon. Okay? Not the most exciting video. Thank you for watching, gang. Make sure to like and subscribe. What we're going to be talking about next, right? You were probably wondering why I wasn't just drawing NH2 and COOH. We're going to talk about how, right, amino acids, they're amphoteric. They can act as bases. They can act as acids. They can look differently their charges can look different based on what type of pH environment they're in. We're going to talk about that in another video. So make sure to check that out if you're interested. And regardless, I'll see you all in the next video.